What's up, guys? It's Mr. Brengle, and today we are going to talk about momentum and impulse. Momentum's something that you guys you've obviously heard that before. Pretty much everybody kind of knows generally what momentum is, if something has a lot of momentum or a little bit of momentum, but what is that exactly? Momentum is a measurement of movement, and it is specifically your mass multiplied by your velocity, or some object's mass multiplied by its velocity. So to have momentum, you must have velocity. So kind of point that out there, highlight that, the velocity part of that. Because if you don't have velocity, then of course when you multiply anything by zero, it becomes zero. So I do want you to be aware of this right here. If you see that symbol, remember that the triangle is the Greek letter delta, and that means the change in. So this is the change in momentum if you see delta P. Why is the symbol of P? Don't ask me. But M is already used up with mass and molarity. So now looking at units here. So for mass, we know, which would be this right here, we know that those units are kilograms. And then for velocity, we know that those units are meters per second. So when you multiply them together, it is natural that they would come out to be a kilogram times a meter per second. Okay, or you might also see it written like this: kilogram times a meter, and then just all of that over a second. So I just want you guys to be comfortable with seeing it either way and recognizing what it is. But that makes sense, right? It's mass times velocity, kilograms times meter per second. Okay, so now on the flip side of this here, we have something called impulse. Okay, so impulse has a symbol of J. Sometimes you'll see I, but for the most part it's capital J. That's what we're going to use in this class. So let's actually come down here to the bottom here, and let's look at this first. So how does an object gain or lose momentum? Okay, so let's think about what momentum is again. Okay, so remember that momentum is mass times velocity. Okay. So how do we change its momentum? Well, if the object's already moving, you could change its mass. That would work. If it's not moving, then changing its mass won't change its momentum because it's zero. But if the object, whether it's moving or not, if you change its velocity and accelerate the object, then it will have a change in momentum. Okay, so in order to accelerate an object, I have this highlighted here, a net force must be applied to the object for some period of time. Okay, I have that highlighted for a reason. Let's go look at the equation for impulse. Impulse, J, is equal to force times time. And this is specifically a force that's applied to an object for some period of time. This is the time that this force was applied for. Okay, so now let's go back and read that again. A net force must be applied to the object for some period of time. That is another way to say that an impulse must be imparted on that object. Okay, so an impulse causes change in momentum. That is super important. Okay, impulse causes change in momentum. So let's go actually. Well, before we jump in, we're going to do a little demo here, but let's come back. Let's come back to this real quick. I want to talk about one more thing. So for the units here, force measured in newtons, and time is obviously measured in seconds, and so that means that the units are newtons times a second. Okay, now I wrote this over here on the side, F equals ma, because I want to go back and look at these units of newtons. A newton, we know that force is measured in newtons, is equal to a kilogram, that's mass, times acceleration's units, which are meters per second squared. Okay, so a newton is a kilogram times a meter per second squared. Now, if we go back, you might think, wait, didn't we just say that? Well, momentum is kilogram times meter per second, mass times velocity. Force is mass times acceleration, so kilogram times meter per second squared. So why does this matter? Well, let's simplify this even more. Let's go ahead and plug in kilograms times meter over seconds squared, that's what a newton is, times a second. Well, what happens here? This second and the squared cancel, and all we're left with is just kilograms times meter per second. That's what this equals. So those are the same exact units that momentum has. So if impulse has the same units as momentum, then that means they're really the same thing. So when we say that in order to change an object's momentum, we must impart an impulse, it actually turns out that whatever impulse you give the object is going to be equal to that object's change in momentum. So impulse is equal to change in momentum. Okay? And this is really what we refer to as the impulse momentum theorem. Okay, so I'm going to go through some of that with you and show you why they're the same with the equations and talk about some different things. But before we do that, let's just focus on momentum and impulse real quick. And let me show you this little activity here. We've got a space dude. His name is Wally. So we have Wally here, and he has a fire extinguisher in his hands. And what I can do is I can increase the force that fire extinguisher is applying to him. Let's bump it to 200, and I can change Wally's mass. Okay, so you guys can see force here, and then I can activate that and let it go for a certain amount of time. So I can give an impulse to Wally using the fire extinguisher, and that then changes his momentum, and we can kind of measure that down here. We'll kind of talk about that. So let me just start right here with Wally's mass at 35 kilograms. We'll leave the force at 200. Let's just try to let this, I'll fire the fire extinguisher for 2 seconds. Okay, so pretty close there. And then what's happening over here is we have a known distance between the photo gates. Why are there photo gates in space? I have no idea, but there are. They're 10 meters apart, and then it calculates the time that it took for Wally to go from one to the other, similar to what we did in the hockey lab. So what that does is if we have a distance and we have a time, we can then calculate Wally's velocity, and this program has already done it for us, and then multiplied it by Wally's mass over here, and that gave the momentum. So Wally gained 415 kilogram times meter per second of momentum. Okay, now let's do the same experiment, but we'll bump his mass. We'll bump Wally's mass to, let's say, I don't know, how about 70? We'll go for 2 seconds again. Okay. And you guys can see down here that the momentum that's gained, the program's cheating a little bit here. You can see it hasn't actually done this over here, but it can already tell you how much momentum. But the momentum gained was 403. Well, Wally's mass increased, right? So the same impulse was given to Wally. It was still 200 newtons of force for 2 seconds. So his change in momentum should be the same. Well, his mass increased. So what had to decrease there to balance that out? The velocity, right? So if we go back to those equations there, and we look at momentum, it's mass times velocity, right? And if his mass went up, then his velocity has to decrease to keep the momentum the same, right? So you can see that the time over here that it took him to get through those gates was a lot longer. Let's just do it. Let's do it one more time here. So we'll bump it up, say to, okay, 90 is as high as I can go for his mass. Let's activate it. Okay, man, I'm on it. Accuracy here. Okay, so you guys can see once again, we're right at 412. So obviously the momentum that he gained theoretically would be the same for each of the 3 trials that I did. But because it's some human error with the timing here, you're going to get slightly different values. Okay, but I was pretty close on all of them. So the momentum gained is about the same. You can see that the photogate time went way up again. It's now in the 2000s, and that's because of Wally's mass being increased. His mass is increased means that his velocity must decrease, so he's obviously moving a lot slower through this if this time increases, right? So just a little bit of a demo there for you, and so that you can see how when I give an impulse to Wally, and I never change that, this number is always the same, the momentum that's gained, because it's directly correlated to that, okay? And that is what we call the impulse momentum theorem. So let's go back to that. So I have some equations here Impulse is equal to force times the time, so the fire extinguisher and how long we applied the fire extinguisher for. And then Wally's change in momentum would be equal to mass times velocity. And I've actually included this change, this delta sign here, because when we say change in momentum, something had to change out of these two values, mass or velocity, right? Now, in like all the problems that we do, it's going to be the velocity, right? But theoretically, you could change the mass of something. You could have a cart rolling on a track and take a mass off of the cart while it's rolling. But for our purposes, this delta sign is typically applied to the velocity, okay? Now, let's set them equal to each other. Impulse is equal to change in momentum, so we could actually go even further with that, and we could say that F delta t is equal to the change in the object's mass times velocity. Okay. Now, why are those things equal to each other? Let's actually go back over here and let's look at this equation. We mentioned it on the last slide. Force is equal to mass times acceleration. Remember that acceleration is just velocity, or an object's change in velocity, divided by the time that it took for that change. So let's rewrite this actually as force is equal to mass times change in velocity over change in time. Okay, so that's just another way to write acceleration, change in velocity over change in time. Well, now let's multiply by change in time on both sides to get that off or out of the denominator. And do you guys see what happened? What just happened here? We cancel this out. F delta t is equal to m delta v. That right there is the equation, right? Impulse is equal to momentum, or change in momentum, okay? Now, I want you guys to think now how this can be applied to real life. And that is in pretty much all the safety equipment that you can think of that would, like safety equipment for impact, okay? So airbags in cars, helmets for bikes, for football, bungee cords for like rock climbers. Maybe nylon cord is the better thing to. I'm not sure that it's actually bungee cords, but the idea is the same. Well, why is this, right? Why do we have these things? It all has to do with impulse and momentum. So what you want to do here is, in terms of force of impact, if you're in a car crash, you feel the impact of the crash, right? Well, the airbag lessens that impact on you, the force that you feel. And it's not that it changes the force of the actual impact, the car crash, it's just decreasing the average force that you feel, okay? So, and that has to do with the time of impact. So let's look at these equations here, and I'm actually going to rewrite this over here. I'm going to write delta P is equal to F delta T. Okay, so change in momentum is equal to impulse, force times time. Now, in it, let's take two car crashes, identical car crash. They each have the same change in momentum. Okay, so I'm going to do two examples over here. So I'm going to write another one out, F delta T. Okay, now the change in momentum is the same for both. It does not change. Now, when you have an airbag, what that does is it increases the time that your head is impacting something, right? So if you didn't have the airbag, you would just snap forward and your forehead would smack your steering wheel or your dashboard, and it would bounce back. It would be a very quick smack, but we all know that if that actually happened, that would really, really hurt and could potentially kill you or seriously injure you. So the airbag increases the time that your head is in contact with something. So if in that situation, the first situation, we have a really small time where there's no airbag, right? And in the second situation, we have a larger time where the airbag has deployed and is increasing the time that we are feeling the impact of the crash, right? So, well, if the change in momentum is the same for both of these situations, the only way for that to work is that the force has to do the opposite thing of the change in time. So if you have a small change in time where your head just smacks the steering wheel or the dashboard, then you're going to feel a huge force. You're going to basically get the entire force of that impact all at once while your head is in contact with the steering wheel. Whereas with the airbag, it decreases the average force that you feel by spreading it out over a longer period of time. So, and that can be, it can be hard to understand because it's not changing the actual force of the impact itself. It's just changing the force that you feel, okay, by decreasing it's making the average force lower. Now, I want you to think about it like this. So we know average velocity, right? So average velocity is your total distance divided by the total time that it took to go that distance. Well, if I run 10 meters in 1 second, I have a really high average velocity, right? I had to be moving very quickly on average to do that. Versus if I had 10 seconds and I went 10 meters, well, then I only covered 1 meter each second, right? I have a lower average velocity. This is the same thing. You increase the time that force was applied for, it's going to decrease the average force that's felt by the person. Okay, so this is very practical and useful for us in real life, and I think that you'll start to see examples of momentum and change of momentum all over the place once you start thinking about it. So that's just a brief little intro to impulse and momentum. We will actually talk about collisions and different types of collisions more in depth in another video.